Right, so that's it. Let's move on and start like today's lecture, which is about classification. And we already know like a few things about classification when we were learning like neural networks, when we were learning convolutional neural networks, and when we were doing training of these neural networks. Right. So classification is it's like a standard computer vision, or you can say machine learning problem. And the idea is you are given some set of data, right? And what you have to do is you have to assign a certain class to each data sample. And you might have like a certain set of classes. For example, you might have 10 classes in your classification problem. Then the task is, given a sample, you'll have to assign one of those classes to that particular sample. So it's just a simple categorization, and there are different variants of this. So the basic one is binary classification. So you just have to decide between two classes to which of these this particular sample belongs. And it could be like a yes or no question. So you can ask that, for example, you have an image and you have a binary classification problem where you say that I want to categorize whether this particular image is of a digit or not. Okay, so that's just yes and no question. And given an image, you will say whether this is a digit or this is not a digit. So that's simple binary classification. Then the second is multi-class classification, which means that you have multiple classes. So for binary classification, you had just one class, right? That's digit. So you are just saying digit is present, digit is not present. But in multi-class, you will have several classes. For example, again, considering the same problem, you are saying that, okay, you want to find out which digit is present in this particular image. Okay, so if 9 is present, you will say, okay, 9 is present, 8 is present, so on and so forth. So then you will have multiple classes. Now, another category of classification is multi-label classification. All right. So in multi-label, in one of the image, you can have two of the categories. So for example, in your input image, if you have both digits 9 and 1. So for classification, you will say both 9 and 1 are present. So that's like again a special case of your multi-class classification. All right. Now let's just consider a two-class classification problem. And so what will happen is you will have your data, then you will have to extract some kind of features from that data, right? Or you can use just the raw pixel values. Then let's say you have features for your data which are two-dimensional, and those two-dimensional features you can plot on this kind of Cartesian coordinate system, right? So for example, in this particular case, we have two classes. The first one is blue, the second is orange. And when we are plotting those features on this two-dimensional map, so it looks something like this. So now the task in classification is to draw a boundary between these samples. All right. So now what's going to happen is once you have this boundary, this is called your decision boundary or your classification boundary. Now all the points during your test time, if they lie towards this side of the line, you can easily say that particular data sample is from the blue class. And if it's lying on this side of this line, then you can easily say it's from the orange class. Okay. Now, classification you can use for a lot of different problems. For example, as we were just discussing, we could have digit classification, right? You want to figure out like which particular digit is present in this image. And we have multiple data sets for this problem, and these are standard data sets. So for example, we have MNIST, which has I think around 60,000 images. Again, we have multi-MNIST. So in this multi-MNIST, we might have multiple digits present in the same image. So that's basically used for multi-label classification. And we have SVHN. This is I think street view house numbers. So these images are like from the house numbers on the house plate, right? So these are colored images. Again, they will be like digits present, but this is like more realistic scenario. And these are some sample images from this MNIST dataset. These are just grayscale images. Now, other problem can be like of this object classification. So this object classification is like you will have an image. It could be grayscale or RGB. You will have to identify which object is present in this particular image. And of course, like to solve any problem, you need some data set because you have to define like what will be your training data, what will be your testing data. For classification, how many classes will be there. So these are some standard data sets which you should know about. The first one is CIFAR 10. So this one has RGB colored images. I think a very small resolution, 32 cross 32. And it's saying 10 because there are only 10 object categories in this particular data set. And this is like extension of this. In this case, we have 100 different classes. And then we have a large scale classification data set that's called ImageNet. And you already might know about this when we were looking into convolutional neural networks. So this ImageNet has again colored images, RGB, and there are 1,000 different object categories. And there are, I think, 1.2 million images, but the latest one has even more than that, 14 million images. So that's a lot. But the original version, which was, I think, launched in early last decade, I think 2008 or 9, it had 1.2 million images, around 100,000 testing images, and around 1,000 object categories. So that's that. Now let's talk about just this problem of object recognition. Okay, so the problem will be you will be given an image, and this I think we have also covered in some of the previous lectures. So given an image, you have to figure out whether this image has a particular object. So in this case, if a person is present in this image or not. Right, so all these are like positive samples, and all these are negative samples. So if this is a binary classification, then it will be just a yes and no answer. So that's so yeah, these are some more details about ImageNet. So there are around 1,000 classes which are derived from this WordNet hierarchy. So this has like almost all the object categories, adjectives, and all those things which we use in our natural language processing. So they picked like some 1,000 classes from that hierarchy. So 1.2 million images, 100K for testing, and a good way to evaluate like how good your classification method is doing is computing accuracy, right? So accuracy means like you will make some prediction about the image, and based on whether it's true or not, you can easily compute your accuracy. Okay, so another good thing to a good way to evaluate your method is looking into the error rate. So top K error rate is like what you will do is instead of making one prediction, you will make 5 predictions, and then you will see like whether your prediction is wrong, correct or not. Okay. So for classification, again, so you'll have some training images which you will use to like learn some kind of model. So for example, if you are training a neural network or a CNN network, so you will train that classifier, but you don't have to train like your method every time. You might have some method which doesn't require any training, and we will look into such classifier today. And then you have validation images which you can use to like find the error in your network, and you can tune like some hyperparameters if you have those in your network. For example, in CNN neural network, you have lots of hyperparameters like how many neurons to use, which activation function to use, which loss function to use, what should be the learning rate. So then you can use this validation image, these validation images to tune those. And finally, you have testing images on which your method will be evaluated. And of course, like before like this deep learning, this is a concept from like I think machine learning. So you can do cross validation, and the idea here is like you divide your training data into multiple splits, and you do that randomly, and then one of the split is used for validation, and then you select like each split as validation several times, and then you take like some kind of average. So, but that's fine. You don't have to know that if you're doing deep learning, because you just train your network once. You don't have to train it multiple times. Now, this was the full process of which we have to perform when we are doing classification. And the idea here is you will use your training images, and depending upon what method you're using, you will always have to extract some kind of features. Okay, and then using those features, you will have to train your method if it involves some kind of training or not. So this will give you the trained classifier. And to training your network, you need some kind of labels. And those labels are used to compute the loss function. Then in case of your neural network in CNN, you use that loss to update your network parameters. Okay, and then once you have the trained classifier, during testing time, you will use an image which the network has not seen during training. You again use the same method to extract the features. You apply this learn classifier and make the prediction. So this is like a general process for classification. So one important step here is how do we extract features from our training data or even like test data. And we have already learned like different ways for this. We have learned like in classical approaches, we looked into like, I think histogram oriented gradients. Then we also looked into SIF features, right? So yeah, these are the different ways which you can use to represent your data samples. You can use your raw pixel values, and this is mainly useful if the dimensionality of your data is not huge. And you can do that even for images. For example, you can do this for your MNIST data. MNIST images are like digit images, which are 28 cross 28 or 32 cross 32. So you can, and they are like grayscale images. So your feature vector will be, I think, 784 or around that number. So it's not that huge. So using raw pixels is fine. You can use histograms, you can use templates, and we have already looked into SIFT and this just we studied HOG. So these are all classical approaches. We also studied like autoencoders last time. So you can also use autoencoder to extract the features and use those features. Okay, and we will also see like complete end-to-end networks where we don't have to extract features. We just use a network which will do the extraction for us while we train the network. Okay, so that's that. Now, the important thing was we need labels for this, which are used for training. And we can generalize the network or whatever model we are training for a classification in some form of function. So we call that classifier F, and then the input will be either if it's end-to-end network, it will be directly the image. If it's like not end-to-end, then we'll have to extract features for apples and send those features to this function F, and then the function F will make the prediction. Okay, so that's the general formulation. These are the features that the classifier, which will give you the output. So I think these details we have already covered, so I'm going to just skip these. Okay, that's just training and testing, right? Now, as we discussed earlier, what we have to do is, for example, if we have just two classes, right? So this is the case of just two-dimensional. So we're assuming that our feature vector or whatever features we have extracted for our training data, it's two-dimensional. So x1 and x2, and we're just plotting those. Now, the circles is like class number 1. These crosses are class number 2. Now, the problem is we have to separate these two. So we'll have to draw this boundary. And that's what classification is all about. So we have to come up with a decision boundary which can separate these two spaces. And these are like your training samples. All right. Now, what will happen is if you have a testing sample, for example, from this blue circle, so it will be close to like this cluster, right? Because it belongs to the same class. So it might lie somewhere here. Then you can easily use this curve here or this line here. So it will have some kind of equation, and then you can easily predict whether this point lies towards the left or towards the right, and based on that you can make the prediction. So the important thing is you have to come up with a decision boundary. Okay. Now, if you have multiple classes, for example, you have 3 classes in this case, so what you can do is you can draw these 3 boundaries, and based on like given a testing sample, you will use all these 3 lines and see like where your point falls based on the equation of these lines, and then you can predict like to which category your sample belongs. Now, the one of the simplest way to do classification is like this algorithm. This is called nearest neighbor. Okay, so the idea is these are your training samples, right? So you have blue squares here, and then you have red circles on the right hand side. Then what you do is, given a testing sample, you determine like which is the closest training sample from this testing sample. So you just compute the distance between all these pairs. So in this particular example, this testing sample is at this location. So this one is the closest. So what you do is, whichever class this sample belongs to, you will assign that class to the testing sample. So in this case, this testing sample, you can easily classify this as a blue square. Okay. So it's pretty simple, it's intuitive. And one thing to note here is, right now we are just trying to visualize like in 2-dimensional, but whatever we are discussing, you can easily generalize this to n-dimensional space, because it won't happen that frequently that you have features of 2-dimension, right? So usually we'll have a feature vector which is pretty long. For example, like when we were working with MNIST images, so when you were using like the pixel values, your feature dimension was around 784, right? So then whatever intuitions we have in this 2-dimensional space, that can be generalized to your n-dimensional space. And the only difference will be, in this case, whatever boundary we are drawing, for example, if it's a line, then in 3D it will become a plane. So then it will become a hyperplane. So you can always extend that. Okay, so yeah, so this one is the closest. So you can easily classify this as a blue square. And all we have to do is like just compute the distance between the testing sample with all the training samples. So it's pretty simple. And of course, I mean, we don't need any kind of training for this. So that's also a plus point. So now the question is, let's say we have to use this nearest neighbor algorithm for classification, okay? And we have these samples as our training samples. Blue ones are like the class number 1, red one is the class number 2. The question is, what does the decision boundary look like? Okay, so decision boundary, if you remember, like we just discussed in previous slides, it's like the boundary which you have to draw, which can differentiate or which can categorize your different classes, right? So you have these 3 options, these 4 options. So 45 seconds. Okay, so let me make it clear. The question is, what will be the decision boundary when we are using nearest neighbor algorithm? Okay, I'm not just asking for any decision boundary, the boundary which we will get after we apply nearest neighbor algorithm. Okay, I think most of you got it right, so that's good. Okay, before I go to the answer, I think there are some interesting comments. Let me go through those. Okay, interesting. So the two comments are fine, but one comment is not enough information. So I'm not sure like why you don't have enough information. So the question was, these are the training samples, right? So exactly, I'm showing you the training samples, and then we have to apply nearest neighbor algorithm, right? And then we have to figure out like what will be the decision boundary. So the decision boundary will be like, which should tell you if I have a point at this point. So let's say if this is the decision boundary, then if I have a point which belongs to class blue, then it should be somewhere here. Otherwise, it should be here if it belongs to the red class. So I think it had like all the details. So the answer will be D because none of this is right. And the reason is, for example, if we talk about like the first one, okay. So let's say I have a point at this particular location. So if this decision boundary is right, then this point will be classified as a blue square, right? But that's not right because if I have a point here and if I have to use nearest neighbor classification, then clearly this point is closer to the red dot. So it will have to be classified as like the red circle instead of blue. So this decision boundary is not right. Same is the case with this one. So let's say if you have a point at this point, it's closer to like this red point, right? And this is also not right. So let me tell you like why that's the case. So when you're using nearest neighbor classification, so the decision boundary will be something like we call this a Voronoi, and because what's happening is between any 2 points, you will have to draw a line which equally divides like the region between those two. Okay, then that will be the decision boundary for those two particular points. And you will have to do that for all the points in your training sample. And once you have this kind of region generated, then I think it's pretty simple to apply your nearest neighbor classification, because you know that if it's like in this particular region, then it will have to be of this black dot class, because wherever you put that point, it will always be closest to this black dot. So you're kind of forming regions or boundaries for each training sample. Okay, so none of those options were correct. Okay, so now let me quickly go through like the comments you have. Uh, So Furkan is saying, I meant the distance between most left box to the separator and the distance between red circle must be equal. How can we form a separator? No, you don't have to create a separator between the leftmost box, because you only have to look into the nearest neighbor, right? You don't have to compare the distance between all the neighbors. It's just you have to look the nearest neighbor. Okay, so he's saying you didn't get it. So we haven't talked about support vector machine yet. So you're going too fast. This is not support vector machine. This is just nearest neighbor classification. Okay, so again, so Carlos is saying it's not like logistic classification. So again, we are not talking about logistic classification yet. Okay, so I think we have, right, so The regions will look something like this when it's a 2D space. And if it's a 3D space, it will look something like this. So instead of like flat regions, you will have a spatial region, like enclosing each of your points. And what you can do is that then you can actually combine all these grayed out regions and also combine all these white regions. And then it's pretty simple. Like you just take a testing point. If it's in the white region, that's a black dot. If it's like in the gray region, that's the red circle. That's the red dot, right? And again, so this is just showing like in 3-dimensional, you can do that for n-dimensional space as well. So that's called Voronoi partitioning. And okay, so another interesting question from Zhengtai, and I think this is a good question. He's saying that these two data distribution is different. In quiz, the dataset is just two parts, but in this example, both classes merge together. But that's fine, right? I mean, if you can create these regions for these like merged classes, you can also do that for your well-separated samples, right? It's far more easier. So for example, in this case, what if you have all these, so I'm drawing a boundary here, if you're following my red pointer. So all the points above this are, let's say, red. Then you will still be able to do this, right? It's just like showing an extreme case. So did that answer your question, Zhengtai? Okay, I hope it did, but you can comment back if it's not clear. Okay, so that was nearest neighbor, and the idea was you just look into like the closest neighbor of the testing sample. But the question is, can we do a bit better? And the answer is yes, we can use like a k nearest neighbor. So instead of using like just one neighbor, what we do is we make the decision based on k nearest samples. So what it will do is it will make your classifier more robust, because in nearest neighbor, if you have some kind of noise, then you will get like very arbitrary results. So then what we do is, for example, if this is your training data, you have two classes, then the nearest neighbor will be same as like one nearest neighbor. So these black crosses or black plus signs are your testing sample. So in this case, the closest one is this red cross. So you classify this as red cross. And for this testing sample, the green circle is the closest one. So this will be classified as a green circle. Okay, so that's similar to what we discussed earlier. But now let's look into three nearest neighbor. So in this case, what we will do is we will find like three nearest neighbors which are like closest to the testing sample. So in this case, you can see that you have this green circle, again this green circle, and this red cross. So this plus sign will be categorized as the blue circle because two of them are green. All right. Same with this one, two of them are green, so this will be categorized as green. So if this were like kind of an outlier, then you can see that you were classifying this as a red cross, which was not correct in case of one nearest neighbor, because you can also see that this is like close to your blue, your green circles, right? So in case of three nearest, you can see that you are classifying them correctly. And you can also do like five nearest. You can increase the number of k. It will just make your classifier more robust. But the only drawback is it's also increasing your computation cost. So in this case, you can again see that. So for this one, you have three greens, two reds. In this one, again, three greens and two reds. So again, this is like classified as green. So if you will keep increasing this, you will see like how this is switching. Okay. Okay, so question from Jengtai, I think it wasn't clear. So In quiz, if the distance between decision boundary and data points of two classes are equal, distance between decision boundary and data points of two classes are equal, then C should be right. Okay, let's clarify this. Okay, so you're saying that but that's a big assumption, right? And that's certainly not true, definitely not true, because you will have a point, you could have a point at this location which is closer to the red dot, right? This point is like towards the left of this curve, which will be classified as blue, which is clearly wrong. And you can look at this location as well. So this point is closer to the red dot, right? I mean, the question is to forget about like those instances. The point is, in nearest neighbor, your decision boundary cannot be a straight line or a curve. It will have to be like that Voronoi plot which I showed, Voronoi regions, right? So for these 2 points, right, your decision boundary should be like something like straight line coming from the top going to the down, right? Not a curve. So something like this, and it will stop at a point where you're seeing that the distance between the that point and the blue dot is actually smaller than this dot. Then then from that point onwards, you will just create another boundary, maybe between these 2 points, right? And then maybe at this location, you'll have to create a boundary between these 2 points. So it will always be a straight line, kind of a zigzag straight line. So that's the main point. Okay, so, and that's exactly like what is being shown here. The boundary will be straight lines, which is clearly dividing the region between 2 training samples. So this is like, so that's the k nearest neighbor. Again, it's pretty simple. And now let's come to the algorithm. So what you have to do is, given all the training samples, you'll have to extract the features, right? Independent of like what method you want to use, you can use pixel values, you can use HOG features, you can use SIF features, whatever features you want to use. So get those features. Now use the same method to extract features for the testing sample, and then simply find the distance between the testing sample and each of the training sample. All right. So once you have all these distances, you have to do nothing but just sort those distances. Okay. And once you have sorted those, then you will know like which of the samples are closer to the testing sample, and depending upon what kind of variant you want to use for nearest neighbor. If it's one nearest neighbor, you just pick the top one. If it's 3 nearest neighbor, you pick the okay, based on whatever value you want to use for k. So one interesting thing to note here is that k should never be an even number. It should always be odd, like 1, 3, 5, 7, 9. And the reason for that is, if it's even, then you might have a scenario where there is a tie, right? So if you have, let's say, 4 samples, then what if like 2 of the samples belong to one class and 2 of the samples which are closest belong to the other? Then you will not be able to decide. So k should always be an odd number. Okay, so the benefits of k nearest neighbor, you have seen it's pretty simple, very easy to implement. You don't need any kind of training. And it's pretty versatile when you can use it for classification. You can also use this for regression and search problems. But the issue is, if you have large number of samples, for example, if you have ImageNet dataset, so running k nearest neighbor on ImageNet will be very time consuming, because what you'll have to do is, as you saw before, there are like 1.2 million images, right? So you'll have to compute the distance between each of the testing sample to all of those samples. And you won't have like just one testing sample. Again, in that particular case, you had 100K testing samples, right? So that's a lot of computation. And another issue is that if the dimensions of your features, that's huge, what's going to happen is you'll have to spend more time in computing the distance. So for example, if you're just computing the Euclidean distance, then if the dimensionality is big, then that will also take some time. So another quick note here that the similarity measure or the distance between 2 points, you can use any measure. I mean, it could be Euclidean distance, it could be just L1 distance, it could be cosine similarity. So you can use different variants of that. All right, so that's all about K nearest neighbor or nearest neighbor. Any quick questions before we move forward? So I think there was a question from Gayur. So the question is, so the circles that you are drawing from KNN examples are similar to Voronoi regions, right? Circles that you are drawing. I'm not sure. So what circles? I mean, we are not drawing any circles, right? So can you clarify that, Gayur?
Professor, can you hear me?
Yeah, yeah.
Yeah, so what I was trying to say is that in the example where you gave us a few slides before, when you were drawing the regions around it, and then you're making a decision,
Mm-hmm.
I was trying to see whether that was similar to what we were talking to what we were saying about the Voronoi decision regions, where we see a certain region around that particular sample, and then we make a decision.
Right, exactly. So what will happen is you can easily draw a Voronoi region around this sample. It will look something like this, right? A straight line here, then a straight line here, straight line here, like this, right? But the point is like these two are the same classes, so you don't have to draw that. You just need this decision boundary. So,
I see.
right? So even in this case, let me go to, so I mean, even though we have drawn like these boundaries around each of the sample, but we don't need all of these boundaries. For example, we don't need this boundary. So what we can do is we can easily remove like all these lines which are between similar colors, for example, between white regions, right? We can get rid of all these, like all these here. And we can also get rid of these boundaries which are between gray color. So then what will happen is you will only have two regions. One will be gray, one will be white. And then depending on where your testing sample falls, you can easily determine which class it belongs to.
Okay, that makes sense. Thank you.
Right. So that was nearest neighbor. Now let's look into like linear classification. And again, these are like the same training samples. Now, linear classifier means you will have to draw a linear decision boundary. So if you draw a line here, separating these two categories, that will be like a linear classifier. And KNN is not a linear classifier because the boundary is not linear, right? It was complicated. So if I draw a boundary like this, then I can say that this is a linear classifier. And if it's two-dimensional space, it will be equation of a line. Okay. And depending upon like where your testing sample falls, you can easily categorize like whether it's a blue square or whether it's a red circle. Now let's look into this into more detail. So for example, we have two categories. We have these fill dots and these circles. So you can simply draw a boundary like this, okay? And it seems like a reasonable solution. If a point is towards this direction, that will be the circle. Otherwise, it will be a dot. And there can be many such decision boundaries, right? And all of these are correct based on this training data you have at hand. So all of these decision boundaries are fine. Now the question is, which of these decision boundary will be like the best to choose from, right? And clearly, if you look into this line, which is touching these 2 points here, also touching these 2 points here, this doesn't seem like a good solution. And the reason is, for example, I have a testing sample, let's say a dot at this particular location, right? So by visually inspecting, we can say that, okay, if it's at this location, it should be from this class because it's like closer to all these points, right? But based on this decision boundary, this classifier will assign it to these circles, which is not kind of right. But based on this training data, it's right. But by visually inspecting, we can say it's not right. So then, I mean, clearly this is not a good decision boundary. So what we can do is we can try to define some kind of margin between the decision boundary and the samples which are closest to that decision boundary. All right. So let's say I draw this decision boundary. What I will do is I will find like the nearest point of this particular class, this dot here, and I will see like how far the dot is from this line. I will just check the perpendicular. And similarly, I will find the same distance for this class. So that's the dot, that's the circle which is the closest, and I can find this distance here. So that is called like margin of a classifier, okay? And the goal is if we increase this margin, and what if we get like the maximum margin which we can based on the training data, then that will be like the best decision boundary we can get from this kind of data we have. And if we look at this particular decision boundary, so a line going from the center of this region will be the decision boundary. And you can easily see that the margin in this case, it's kind of maximum. You cannot increase it further. Okay. So this is called a maximum margin linear classifier. And it's called linear because you have a linear decision boundary. Okay. And it's also like the simplest form of SVM, which you can say, which we can also say as like linear SVM. All right. So these are called support vectors. And this distance, this perpendicular distance from the support vectors to the decision boundary, that's called the margin. And the total margin will be like just twice of that. And that's the intuition behind maximum margin classifier or your linear or your non-linear support vector machines. So let's see like what else we can cover in this topic. So the background is it's like a very general approach for classification problem. It's also used for regression. And it was developed around like 1990s, and it has grown in popularity. That's fine. So it works well for like most of the scenarios. Now, one interesting thing to note about this is before SVM in like early 90s, neural network were like a big deal. I mean, they were very popular and everyone was like crazy about those, right? Then SVM came, and then the research in neural network went down. So it was like because of SVM, the boom which we are seeing like in deep learning these days, it was kind of delayed. It later came on in like 2012. So I mean, that's a joke, but it could have been happen like if researchers wouldn't stop, were still like working on neural networks with that enthusiasm and not looking into like SVMs, then we might have seen that boom in deep learning maybe before 2012. So I think even after like 2012, people were still using SVM, and even today, like people use SVM along with deep learning. They extract feature using deep learning and use SVM as a classification model. And in most of the cases, it actually performs better than neural networks. So that's a quick background on SVM. So that was actually the second dark time for neural network. The first one was, I think, around 70s or around 75. There was similar story around that time as well. So for SVM, I think there are different versions. So the most advanced is like support vector machine, which we call SVM. But before that, like there were other versions like Max-Margin Classifier, which we just covered, where we try to maximize the margin. Then we have like support vector classifier, which is again like same as maximum margin, but with like some slight differences. Okay, so what's going to happen is maximal margin classifier is in two-dimensional space, you will draw a line, but if it's n-dimensional space, you'll have to draw a hyperplane. Okay, so the rule is like if you have a n-dimensional or a p-dimensional space, then your hyperplane will be like in p minus 1 dimension. So it's same as like if you have 2D 2D data, so you just have a 1D line, right? And if you have a 3D data, then you will have a plane. So we also call that 2D plane. And this is like the general equation for your hyperplane, depending upon like depending on the dimensions. So we'll have these different variables for 2D. That's the equation, right? You can easily represent this line using this equation. And what you do is based on like if you put in like any of these points in this equation, you will get like either a positive or a negative sign. So you'll get some number. It will be either positive or negative. And based on that sign, you can easily determine whether the point is like in the blue region or in the red region. So in this particular case, like for this line, we have this equation. So that's fine. Okay, so let's do this. Let's stop it here. And I think it will be good if we cover this next time.